This is Angela Galloway, and this is actually going to be our last lecture video for STA220. This is Chapter 10, Section 2. So we've already looked at hypothesis test for population proportions, but now we're going to look at, how to do those tests for population mean. So when we did confidence intervals, remember for means, we had to use the t-test, or we had to use t statistics instead of the z. So the same thing's going to happen for our hypothesis test. We're going to have to use the t instead of the z. Now, because of that, we're not really going to be able to memorize the values for the t's as easy as we would for the z. So remember when we did the critical value approach back in the last section, we could kind of memorize that 1.645, 1.96, etc. For some of the critical values. But for these, since we're going to be using the t, we won't really be using those values anymore. So the critical value approach isn't going to be as simple because we'll have to go back to the t-chart. But the p-value is difficult to get with the chart. You don't actually get an exact p-value. You get kind of a range for your p-values. But if we're using our calculator, the p-value is going to be given just like it was given for our population proportions. So, using the calculator, we can get the p-value fairly simply. All right, so using the t-distribution, if you're asked to find like the critical values or whatever in your homework, then this is what it's going to want you to do. Find the critical value for a right-tailed test, so we're up here in the right tail, with a sample size of 20 and alpha equal to 0.05. So since the sample size is 20, our degrees of freedom is 19, so we're going to go to this row here. And then our alpha is 0.05 in the right tail. So we're going to go to 0.05 and we'll see that down here, let me get to this, it'll be a little easier for you to see. Down here, we've got 19 and 0.05 and we get to the 1.729 right there. And so that's our answer. Find the critical value for this test. So we've got alpha equal to 0.1, degrees of freedom is 14. Okay, so you notice this one, the alternative hypothesis is that mu is less than 5. So that means we're going to be on the left side over here. And remember, just like z values, z's are positive over here and negative over here. The same thing with t's. So this chart only gives positive values. So if we're talking about the left tail, we have to make it negative. Okay, so if we're looking at 14 degrees of freedom, we're up here, right, in the 14 row. Alpha is equal to 0.1, so we'll go to 0.1 up here, and 14, we get 1.345. But because we're on the left side, we make it negative. All right, find the critical value for this test. This is a two-tailed test, right, the not equal to. So when we have alpha, we need to divide that by 2 so it can go in both tails. So 0.01 divided by 2 is 0.005. That's what's going to be in both tails. We've got 24 degrees of freedom, so we're going to be down here at 24. 0.005 is here, so we'll go down here and get 2.797. All right, and so when we're doing a not equal to test, we're going to have a positive and a negative, right? Because our value could fall down here or it could fall up here. So we have a negative and a positive. Now, why I said the p-value was difficult to find with the chart was because of this. Okay, find the p-value for a one-sided test with t equal to 2.2 and degrees of freedom of 19. All right, so let me get my eraser here so I can erase some of this off and we'll start again here. Okay, so degrees of freedom of 19. So here's our degrees of freedom of 19, right? This row here. Now, when we're using, whoops, when we're using the t-chart, let me erase that there. When we're using the t-chart, it doesn't give us every possible t-value, right? It just gives us the most common areas, right? So these are the most common areas that we're interested in, or alphas or alpha halves. So those we're going to use to find the t's that go along with them. In our normal chart, we have pretty much every z value and we can find the area associated with it. Here, we only have a few of those areas given, so we're not going to have every possible p-value. So here, if we've got degrees of freedom of 19 and the t is 2.2, all we can do is see where it falls. So 2.2 you see is going to be very close to this number, but really it would just be between these two values, right? Between 2.093 and 2.205. So we'd go up here and say that our p-value is going to be between those two values, right? So it's going to be probably a little bigger um, than zero point zero 0.02 and smaller than 0.025. Okay, so that would still give you enough information. Like if we had an alpha of zero point 0.5 and we're trying to decide are we going to reject or not, we would still reject whether the p-value is 0.02 or 0.025, right? So most of the time that's going to be enough information to get it in a certain range so you'll still know is that less than 0.05 or zero point zero 0.01 or whatever. So that's how you would find the p-value with the chart. But when you're working with your calculator, it's going to give you an exact p-value. All right, so looking at an example here, a certain company wants to test to make sure the bags of sugar they are selling really have a mean weight of 2.5 pounds. They take a sample of 101 bags of sugar and find a mean of 2.47 pounds with a standard deviation of 0.56. At alpha equal 0.05, is this enough evidence to say the bags of sugar do not have a mean of 2.5? So usually when we see that do not have or different, we're going to do the not equal to for the alternative, and so that would be a two-tailed test. This is the weight that they want the bags to have, right? 2.5. So that's going to be our null and alternative mean. So mu is equal to 2.5 and the mu is not equal to 2.5. Our test statistic here, if we were doing this by hand, we would do t equals x bar minus mu sub 0 over s divided by the square root of n. We plug in our values here and we get negative 0.54. Now if we're doing the critical value way, we would go back and find degrees of freedom of 100 and 0.025. So we're at 100 and 0.025 right here, 1.984. Because we're at 100, we're getting pretty close to the z, right, of 1.96. So 1.984. So since we're doing a two-tailed, we're going to have the positive and the negative. So if a value falls in here or here, then we're going to reject. This one, negative 0.54, isn't very far from the mean, right? It's just half a standard deviation below the mean. So it's actually not very extreme. It's not a very extreme value. It's going to fall inside here, which is the do not reject area, right? So we're going to fail to reject the null at alpha equal 0.05. Or you can do the t-test in your calculator. So let me bring that up here. Okay, so we're going to turn it on. We're going to go to Stat and Tests and the t-test right here, number 2. We are going to input statistics because we have the mean and standard deviation. You use data if you have the actual original data and you want it to calculate the mean and standard deviation. We won't usually have that for our problems. Okay, the mean here from the null hypothesis is 2.5. X bar is 2.47. S is 0.56. And N is 101. We're going to do a not equal to test, right? And then we want to calculate. All right, so we see our t is what we got here, negative 0.54, basically. The p-value is 0.591, 0.592. So that will be the p-value. That obviously is much bigger than alpha of 0.05, right? So again, we fail to reject there. That's not an extreme statistic. Okay, so once you've figured out, how to set up your hypotheses, figure out what statistics you've got, really you just need to know, the t-test, where to go to get those values that you need. So for this one here, we're looking at our null and alternative, our mu equal to 4.5 and mu greater than 4.5. So our null hypothesis is 4.5. X bar is 5 because that's the sample or that's the mean you got in your sample. S is 1.2, the standard deviation from your sample. And N, it says we selected 25 orders. We were interested in seeing if the mean time has increased, so that would be a greater than. So we're going to go over here to greater than and calculate. So we get a T of 2.08. So we're about 2 standard deviations away from the mean, which is kind of far away. It kind of just depends on what your alpha is, if that's going to be far enough away or not. In this case, our alpha was 0.01. Our p-value here would be 0.024. So a small alpha, I mean, that is a small p-value here, but the smaller your alpha, the harder it is to reject, right? So this one, even though it's small, it's not small enough, right? So we're going to fail to reject the null at alpha equal 0.01. If we had had an alpha of 0.05, we would have rejected, right? So you need to determine at the beginning of your test, what alpha level do I want? Alpha is telling us the chance that we're going to make a type 1 error, right? So you just kind of have to decide, is this something that I really want to make sure I'm not making a type 1 error, or is it something that's not going to make too much of a difference? For example, this example here, is it really a big deal if you find out that your wait time really is longer, but it really wasn't? You know, Not really. That's not going to be a big deal if you end up making improvements, even though the true mean hadn't really changed. So, I mean, in this case, I would probably use a larger alpha, because it's not that big of a deal. But if it's something with, a medical procedure, a treatment, or something where you really want to be sure that if you reject that it was the right decision, then you will want to use a small alpha. All right, the FICO scores here, this is going to be a greater than test. When we do this, we're using an alpha of zero point 0.1, so a rather large alpha. There's 10% chance we may make the wrong decision. We might have a type 1 error. Our p-value is going to end up being 0.088, and so we would reject. So again, you're going to do the t-test on that one. This is one that kind of looks similar to your homework. Well, it probably looks like one of your homework ones. So they want us to find the null and alternative hypothesis. So one thing you want to look for is, of course, making sure the numbers are the same. These numbers are the same in all of them, like the null and the alternative. So you want to make sure of that. This says the mean height of women was 63.7. We want to know if today's heights are different than what they used to be. Okay, so 63.7 would be our mean, right? We're wanting to know if women are taller today, which would mean greater than, right? So that's why we're using greater than in the alternative. If the p-value is 0.13, what that's telling us is there's a 13% chance of getting a mean height of 64.3 inches or taller if the true mean height is 63.7, right? So we're saying that, if our distribution is centered at this population mean, 63.7, okay, when we put 64.3 here, so there's our 64.3, okay, um, the chance of this happening, that's going to happen about 13% of the time. So is that unusual? It's kind of unusual, but it's not really unusual, right? It's going to happen 13% of the time. We want to reject anything that's going to happen 10% of the time or less, right? So this one is not to that threshold, right? It's more than that. So we're not going to reject the null hypothesis. There wasn't sufficient evidence to conclude that the height is greater today. Now, is it possible that the height is greater today? Yes. Okay. But we don't have enough evidence here to say that there has been a change. So for now, we can't reject that null hypothesis. Okay, now we don't know if the null hypothesis is true or false. We just know we don't have enough evidence to say that it's not true, with what we did. So maybe we'd take another sample or do something else, maybe get a larger sample size and see if we could compare, in that case. But for now, not enough evidence. All right, so remember with one proportion z-test, for proportions in the calculator, we're going to use one proportion z-test, right? For means, we're going to use the t-test. Okay, just like with confidence intervals. For means and confidence intervals, we use the t-interval, and for proportions, we did one proportion z-interval. Okay, so those are the four things you'll be using in this Unit 5. So on your Unit 5 exam, those are kind of the four main things that will get you through most of your problems. The only things that it wouldn't is like when you're calculating sample size. Back in our Chapter 9 stuff when we were trying to find, how many people do I need for a certain sample, then that is something you would need, that formula for, and you wouldn't do in your calculator, but pretty much everything else you can do using those four commands in your calculator. All right, so that is our final slide for statistics. That is the end of what we're going to learn. And so I hope that you enjoyed this class and that you did learn some new things and maybe some stuff that you'll be able to actually apply in real life. Or at least one day, you can sound smart when you tell people you understand what a margin of error is, or, how to interpret a poll, the difference in means and medians, calculating probabilities. So all those things that we learned, I hope you'll put it to good use. So thanks for taking my class. If you have any questions, please email me at angela.galloway@kctcs.edu. And I hope you do great on this last unit exam, great on the final exam, and have a great future career in whatever you're going towards. Thanks.